Let's go a bit more in depth on examples of Laplace transform, something that is a bit more than the existence or non-existence of the Laplace transform of a specific function. So let's start by Laplace transform of polynomials. We'll start by the easiest polynomial of them all, the zeroth order polynomial, the constant function 1. So the Laplace transform of the constant function is this integral from 0 to infinity of the exponential of minus st. And I hope you can take the integral on your own. S is a parameter, we should not be looking at it. The integration variable is t, and this is 1 over s e at the minus st. There is a minus in front between 0 and infinity. At infinity, for t equal to infinity, e at the minus st is equal to 0. So the only term we have left is the term at 0, where exponential of 0 is 1. So this is 1 over s. Let's go at the first order polynomial, f of t equal to t. So the Laplace transform of t is the integral from 0 to infinity of t times our exponential, the integration kernel exponential of minus s times t. We use integration by part. We use, again, that e at the minus st is the derivative of 1 over s between parentheses of e at the minus st. There is a minus missing in this case. So now we can take integration by parts. We do that and we notice that minus 1 over s becomes a constant that we can take out. Then we have a 0 to infinity evaluation of an integral t at the e at the minus st minus the integral from 0 to infinity of e at the minus st. The first term goes to 0. Why? Because at 0, t is 0, and at infinity, exponential of minus t is 0 itself. Well, the second term is the same term we looked at when we were doing the Laplace transform of zeroth order polynomials. This is great because we know how to handle that. So the Laplace transform of t is 1 over s squared. Let's go to second order polynomials. So t squared. The Laplace transform of t squared is the integral between 0 and infinity of t squared times the exponential of minus st. I would encourage you to pause the video here and work it out. If you do it correctly, you just need one integration by part. And the result of the previous slide, that is the Laplace transform of t and the Laplace transform of 1. I hope you have paused the video and solved it by hand. Then you would have found out that the solution is 2 over s to the third. So, can we do general nth order polynomials? Yes, we can. And the brief answer is that by recursive formula we can find that the Laplace transform of t to the n is n factorial over s at the power n plus 1. Can we prove it? Well, let's take the usual integral with the usual integration kernel. Then, again, let's use the integration by parts. Then we have something very similar as we had before, just that now we have t at the power n, and an n popping up inside the integral. The first term is 0 for the same reasons as before, and we are left with something that is n over s, integral from 0 to infinity of t at the n minus 1, e at the minus st. And this is the Laplace transform of t at the minus 1. So we retrieve that the Laplace transform of t to the n is n over s times the Laplace transform of t at the n minus 1. Recursively, we can find that this is equal to n factorial over s to the n times the Laplace transform of 1 that we have computed already. So we can prove the formula for the Laplace transform of a t to the n. Let's go now into trigonometric functions. We want to prove the Laplace transform of sine of at. We know that the first derivative is a cos at. And we can write the Laplace transform as the usual integral between 0 and infinity, our function, times the integration kernel. We can solve this using twice integration by parts. But there is another way. We can think of looking at another function altogether for a little bit. We look at e, the exponential of at. And we can solve it by hand. And it's this evaluation between 0 and infinity of minus 1 over minus s plus a, exponential of parenthesis minus s plus a times t, where we retrieve 1 over s minus a. When we deal with Laplace transform, we always expect s to be as big as needed. In this case, we need s to be strictly bigger than a. Because of this format of the Laplace transform of the exponential of at, that is sort of a shift, it is called the translation formula. So let's try to use the translation formula in our Laplace transformation of the trigonometric function sine. How can we do this? Well, we can remember that the sine can be written through the Euler formula as the imaginary part of the exponential of imaginary numbers times a times t. And because the Laplace transform is linear, we can take the imaginary part out. But we have just computed exactly the Laplace transform of e to the at. In this case, we just have added an imaginary number in front. Note that while we were doing the Laplace transform of the exponential, we never said that a had to be real. So having a complex value there is no problem for us. Now we want to try to solve this this complex fraction. We do that by multiplying it on the top and on the bottom by s plus imaginary number times a. We retrieve something that doesn't have imaginary numbers at the bottom anymore, just at the top. And this can easily be solved. What is the advantage of using this approach? Well, the advantage is now that also calculating cosine, the Laplace transform of the cosine, will be trivial because we'll follow exactly the same steps, except that instead of taking the real part, we're going to be taking the imaginary part. So these are the same steps as we took in the previous slide, except that at the last step, we take the real part instead of the imaginary part. So we keep s, but we do not keep a.